Bismillahirrahmanirrahim. Assalamualaikum warahmatullah. So, modulation index and percent modulation. So we have discussed about modulation index. Modulation index is term used to describe the amount of amplitude change present in AM waveform. Percent modulation is the coefficient of modulation index stated in percentage. So it is the same. Modulation index is the maximum amplitude of modulating signal over divided by the maximum amplitude of carrier signal. So this ratio, if we multiply by 100, we can get percent modulation, where M is the modulation coefficient. Usually the value is from 0 to 1. Okay, M is percent modulation. EM is the peak change in the amplitude of output waveform. AC is the amplitude of the unmodulated carrier. AC is the carrier, M is the modulating signal. So this is the graphical representation of the relationship of EM, and EC. So we have discussed this before. Vmax EC plus EM, Vmin EC minus EM. Based from the above figure, EM equal to half Vm minus Vmin, EC equal to half Vm plus Vmin. Based from previous figure, so we can rewrite again this equation. M is the changing this value into this value. So we have the modulation index is Vmax minus Vmin over Vmax plus Vmin. Multiply by 100, we can get the percent modulation. EM can also be defined as the sum of voltage from upper and lower side frequencies. EM is the voltage E USF plus E LSF. USF equal to LSF. So USF equal to LSF equal to EM over 2. So this EM divide by 2, half divide by another 2, so we become quarter, 1 over 4. 1 over 4 Vmax minus Vmin equal to E USF. What is this? This is the amplitude of the signal at upper sideband and lower sideband, the sideband signal. The amplitude is quarter V 1 over 4 Vmax minus Vmin, where EUSF is peak amplitude of the upper side frequency and ELSF is the peak voltage of the lower side frequency. It can be seen that the percent modulation goes to 100% when EM equal to EC. Okay, when the value of EM equal to EC, then the modulation signal, the modulation index is 1, or the percent modulation is 100%. At 100% modulation, the minimum amplitude of the amplitude Vmin equal to 0. Maximum percent modulation can be imposed without causing excessive distortion is 100% percent modulation, or modulation index equal to 1. So when modulation index equal to 1, or when the percent modulation is 100, so we will get the value of Vmin equal to 0 here. So there is no value of Vmin. So the Vmin equal to 0 at percent modulation 100%, equal to 100. So the envelope will become like this. So there is no signal. This negative peak and this positive peak will touch each other. So this is the envelope at 100% modulation index. The ideal condition for amplitude modulation is when M equal to 1, or the modulation index, the percent modulation equal to 0, which means Vm equal to Vc. So the ideal condition is Vm equal to Vc or Em equal to Ec, and modulation index is equal to 1 or percent modulation equal to 100%. However, when modulation index is greater than 1, is bigger than 1, then that is called overmodulation. Overmodulation. The overmodulation is present. So what happened? So this will happen. Okay. The amplitude of AM wave varies in proportional to the amplitude of modulating signal, and the maximum amplitude of the AM wave is EC plus EM. Given the arm modulated carrier is VC, EC sin 2 pi FCT, therefore the output modulated wave can be expressed as, this is the signal, the expression for envelope, AM envelope. Peak carrier signal, EC is the peak carrier signal amplitude, FC is the carrier, FM is the modulating signal frequency, EM is the maximum signal amplitude. Okay, so solving this equation, we have done this before. The average power dissipated by a load by a modulated carrier is equal to the RMS carrier voltage divided by the load resistance. So PC is, this is the half power square over R, or AC square over 2R. So this is 1 over SERT2, so multiply, so we will have these two at the below, at the bottom here. The total power distributed during a modulation process is affected by modulation index. So the modulation index is affecting the total power. So total power is P carrier plus P sideband. Okay. The power at sideband, low sideband and upper sideband is defined as P upper sideband, P USB, equal to P lower sideband, equal to M square PC over 4. So M square PC over 4, M square PC over 4. AM power distribution. We know that AM signal has 3 components. We know that the AM modulated envelope signal has 3 components: the arm modulated carrier, lower sideband and upper sideband. So therefore total power of AM is the sum of carrier and power in the 2 sideband. So the total power of envelope is the sum of carrier power, upper sideband power and lower sideband power. So this is the equation. Here all the 3 voltage are RMS value, and R is characteristic impedance of antenna in which the power is dissipated. The carrier power is PC, P carrier, EC over SERT2 square over R. So we have this equation, EC square over 2R. This is the carrier power. The power of upper and lower sideband is the same. So E square sideband over R. E sideband M EC over 2. This is this equation over SERT2. Solving this equation, we'll have M square EC square over 8R. Hence the total power equation becomes power carrier, lower sideband and upper sideband. Solving this equation will give total power PC equal to P total equal to PC bracket 1 plus M square over 2. This equation relate total power of AM wave to carrier power, maximum value of modulation index equal to m equal to 1 to avoid distortion. At this value of modulation index, P total equal to 1.5 P carrier. From above equation, we have m square over 2 equal to P total over PC minus 1. So solving this equation for m, we have m is the set 2 bracket P total over PC minus 1. So example, an audio frequency signal 10 sine 2 pi 500t is used to amplitude modulate signal. Calculate motion index, sideband frequency, amplitude of each sideband, bandwidth required, total power delivered to the load. Okay, solving this. Okay, solving this all, we get the value. Next, example 2, 400 watt carrier is modulated to depth 80%. Calculate the total power in the modulated wave. So P total equal to PC 1 plus m square over 2. Solving this, we can get the answer 528 watt. Another example. Okay. Complex signal modulation. As most of the signal are complex and can be represented by combination of various sine wave, m can be determined by m equal to m effective equal to set of all sum of m square 1 plus m square 2 plus m3 square, and set. Thus total power for this complex signal is Pt equal to Pc bracket 1 plus m effective square over 2. Amplitude modulation by multiple sine wave. In practice, modulation takes place due to multiple modulating wave. Here, let us consider what will happen if two or more sine wave modulate the carrier simultaneously. Let the two modulating sine wave be represented as EM1 equal to EM1 sine omega m1t and EM2 equal to EM2 sine omega m2 1. The total modulating signal can be the sum of these two sine wave, EM1 plus EM2. EM1 sine omega m1 t plus EM2 sine omega m2 t. Solving this equation, we have EC1 plus EM1 over EC sine omega m1 t plus EM2 over EC sine omega m2 t bracket sine omega ct. So now we have this amplitude having combination of the signal sine wave 1 and sine wave 2. So resulting from that, we will have this frequency spectrum where we have two side frequency, lower side frequency, and two upper side frequency. So now instead of three frequency, now we have 5, which is the carrier, and lower side 1 and lower side 2, and upper side 1 and upper side 2. Frequency spectrum of AM wave having two modulating frequencies. The total power in the AM wave having two modulating signal will be written as this, and this can be right the above equation. We can solve this equation, and so we can solve this equation to become this: P total equal to PC 1 plus M1 square over 2 plus M2 square over 2. Compare this equation similar, and we can say that P total equal to PC 1 plus M square 2. So that's all for this chapter 2, part A, AM modulation. That's all. Thank you very much. Assalamualaikum.